So let's take a look at the application of differentiation there. All right, so one of the applications that we need to know for differentiation is for stationary points. Right? We need to remember a few things about stationary points. The first and one of the more popular ones is to identify a maximum point. Right? To identify a maximum point. And then we also have to identify minimum points. Right? These two we should know already. This one here, of course, we know that d2y dx squared is less than 0. This one here, we know this occurs when d2y dx squared is more than 0. But we could also use a first derivative test as well. This function here, right? From here to the stationary point. Is this function increasing or is it decreasing? Increasing, right? So you can see that dy dx here is more than 0 here, up till here, right? And on the next side, dy dx is less than 0. So the derivative test for a maximum point is if the first derivative goes from more than to less than. So if you have a value here, let's call this value b. If you plug in x is equal to a and you get more than 0, and if you plug in x is equal to c and you get less than 0, then you have a maximum point. Okay? So if your first derivative goes from more than to less than, you have a maximum. If your first derivative, on the other hand, let's call this point x equal to b. If your first derivative goes from less than, when x is equal to a, to more than, when x is equal to c, if it goes from less than to more than, you have a minimum point. So all these things you might remember from Form 5. Might. And then new one. What is here? Some stationary points look like this. Yes. Right? A, B, C. A, B, C. Right? Here now, what is here? There's a special stationary point, so the function increasing when it reaches here, it's not going to decrease. It's going to continue to increase. This stationary point here, together with the other way around, it's decreasing. Right? It's decreasing and it continues to decrease. Right? These 2 points here are called points of inflection. How is identify them? Well, one of the ways to identify them is if the second differential is equal to 0. But it is a real name test, right? Because even when you identify the second differential to be 0, you still have to come back to the first derivative test. So you have to check and see if before x is equal to b, let's say you choose x as a, if dy dx is more than 0 here and dy dx more than 0 here when x is c. So when you plug in a again, dy dx is more than 0. When you plug in c, you get more than 0. So no sign change, point of inflection. Or on the other hand, if you have dy dx is less than 0, when x is equal to a, and you have dy dx is less than 0, when x is equal to c, no sign change, you have point of inflection. Okay? So if the sign is not changing for the first differential, inflection. If the sign is changing, then it's maximum. All right? So they want the nature and they want us to find these stationary points. That's okay? So the first thing we do is we find the first differential. Right? So stationary points occur when dy dx is 0. So the first thing we do is we find the stationary points. So we differentiate first. And the second thing we do is we say that stationary points occur when stationary points occur when dy dx or the first differential is 0. So make this equal to 0. Right? Make that equal to 0 and then solve for x. Tell me what you get. So minus 2, 4. All right, so take a look here. We're going to determine, I'm going to use first derivative test because we don't know if those points are points of inflection. So I'm going to use first derivative test and check and see if it's max and min, right? I ignoring second derivative test. Right? As I said, I'm going to ignore second derivative. For now, I'm just going straight to first derivative. So let's check out x is minus 2, right? Let's pick a value more than x is minus 2, but remember, you don't want to go into the boundary 4, right? So just picture this in your mind. So you want to pick values around minus 2, but you don't want to go all the way down here because it's the next stationary point here. So you're allowed to pick values here between any value around here, around minus 2, more than minus 2 or less than minus 2. So let's pick 0 and minus 3. So let's pick a value bigger and let's pick a value smaller. The reason we're doing this is we want to see if there's a sign change in dy dx. No, don't matter. Right? In this case, it don't matter. But suppose these were boundaries. Suppose these were your stationary points, then yes, you want to pick values close to here. Okay? But 4 quite down here. So we can pick anything here. I just pick in 0 and I pick in minus 3. Okay? And for 4, I'll pick 1 and probably 5. Okay? You want to see how the function behave in there. Right? And for 4, I said I'll pick 5 and I'll pick 1. Okay? So our objective now is just to check the sign. Check the sign for f prime x. Of course, when it's minus 2, we know f prime x is 0. When it's 4, f prime x is 0. So let's see. When it's minus 3, put minus 3 in here again, positive 9. 9 by 3 is 27. 27 plus 18 minus 24, I gain more than 0. Check it from now, please. When you plug in 0, again, f prime, right? Again, f prime x will be less than 0. Get that? So plug in minus 3 in here, plug in 0 in here. I got more than and less than. So if the function increasing then starts to decrease, what kind of function is that? Maximum. So therefore, x equal to minus 2 is a maximum. Ideally, you should find the y value as well, right? How about here now? How about here? Let's plug in 1. Plug in 1 in the function. You'll get 3 minus 6 minus 24. So again, less than 0. Then plug in 5. Help me out here now. Right? That is 25 by 3. That is 75. More than 0. So again, less than to more than. Therefore is a what? Are you okay with that? Of course, you didn't have to do this because you could have just do second differential. Right? But just showing you how I set it up for the next one. Right? So the second derivative test, you can do it one time. I was just showing you this one because I wanted to give you 2 examples, right? But the second derivative test, you differentiate this and you'll get 6x minus 6. Then plug in x is minus 2. More than likely, you will get less than 0. Therefore, it's a max. Come here now. Second derivative is 6x minus 6. Plug in x is 4. You'll get more than 0. Therefore, it's a minimum. Or if you get equal to 0, point of inflection, then you come and do this. This one here, I want you to do second differential and then choose the point. right? So you should have your first differential by now, and you will get minus x cubed minus 6x squared. And then remember your stationary points occur when f prime x is 0. So it's minus 4x cubed minus 6x squared is 0. When you solve, what you got? X is what? Negative 3 on 2, 0 on. That's all. Right? So find the second differential. Find your second differential. The second differential is minus 12x squared minus 12x, right? And then we're going to start here. Let's plug in x is minus 3 on 2. X is minus 3 on 2, so f double prime is minus 12 by minus 3 on 2 squared minus 12. So therefore, less than 0, therefore it's a maximum point. Right? Please remember to find the y value. Find the y value as well, right? Plug in minus 3 on 2 here and get the y value. Now, when x is 0, we have a problem. Right? So when x is 0, we have a little problem. We choose f double prime 0 giving us 0. So therefore, a point of inflection exists. Right? We have to confirm it. Right? We have to confirm it. Right? So you're taking when x is 0, you're taking, what's the value you choose here? Minus 1. Right. You can choose minus 1. Can you choose minus 2? Can you choose minus 2? No, because it goes beyond that point there, right? Beyond minus 3 on 2. Okay? Right? And just check it out quick. This is the first derivative test. Huh? This is a first derivative test. Right? So the first derivative here, we know the first derivative here is equal to 0. Plug in minus 1. When you plug in minus 1, I get in a minus n. Less than 0, right? Yeah. Plug in 1 now, again, less than 0 again. That's okay? Yeah? Less than, no sign change, therefore, point of inflection. That's okay? So this graph probably will look like this. It went up to a maximum. It went up to a maximum at 3 on 2. And then when it reached 0, it decreased and then continued to decrease. Probably something like that. I like how this looks. Hold on. So you probably have your point of inflection here. Point of inflection here, sorry, at 0. And your maximum here at minus 3 on 2. So it probably looks something like that. Went up to a maximum inflection. Okay? Question didn't ask you. I want to make sure you understand. If I were to ask you, add this to the list of differentials from last week, right? One thing I keep forgetting to do because they're expected to know this, right? The differential of ln x is 1 on x, right? Generally, if I ask you to differentiate something that looks like this, ln anybody remember why I put in modulus signs here? Huh? Because we could only find one of a positive, right? So if I ask you to differentiate ln f of x is your denominator and your numerator is the differential of it. Okay? So if I ask you to differentiate ln x is the denominator and your numerator is the differential of x. All right? That's it. X here, differential of this here. All right? Let's just do 3 examples in this, right? It's not a popular thing, but You see a differential equation. There's a few of them where you had to learn that. Please differentiate this ln 3x differentiate ln 3 squared plus 1. And last one, maybe add another tricks. Differentiate ln cos x. All right? Let's try those there. Right, so what we have here, 3x in your denominator, and your numerator is the differential of this, which is 3. Right? 3 will cancel and you'll get 1 on x. Right? Here, your denominator is 3x squared plus 1, and your numerator is the differential of this, which is 6x. Here, your differential, your denominator is cos x, and your numerator is the differential of cos x, which is minus. Right? Well, which is minus 10, right? Nice. So I wanted to go over that because I forgot to do that last week. The last thing you want to look at is rates of change. Right? Just a quick reminder, Shivish. Right? When they say rate of change of y, what are you talking about? Shivish? It means dy dt, Shivish. Right? It means dy dt. Right? You want to see how y changes with respect to t. But how do you find these things? You use chain rule, right? So one side is up ty, the next side is up, and the variable goes here. So you find dx, dx. Right? Same thing if you have dp, dt, and so on, right? If you had volume. Right? If you had the rate of change of volume. Here would have been dv, here would have been dt, and sometimes height. So you put dh here, dh here. Right. Let's try this here. A spherical balloon. A spherical balloon is being inflated. So the radius of the balloon is increasing. The radius of the balloon is increasing at a rate of 0.1 centimeters per second. 0.1 centimeters per second. That's the important part, right? 0.1 centimeters per second. So find the rate of increase. Find the rate of increase. Find the rate of increase of the volume of the balloon when its radius is 5 centimeters. When its radius is 5 centimeters. Right? And for number 1, they gave you the volume. Right? The volume is 4/3 pi r cubed. Right. Just take a little reread again. What else they gave you? They gave you dr dt. Nice. That was what, 0.1, right? What else they gave you? dv dt, dv dh by dh. And it said when r is 4, right? And what they asked us for? Huh? R is 5, sorry. What they asked us for? A volume, right? So they asked for dv dt. So what would the formula be for dv dt? dv dr multiplied by dr dt. And we already have dr dt. So it's just to find dv dr. So we need an equation with v and r. So we're going to use this here. We're going to differentiate that. What's the differential of dv dr? 4 pi r squared. How do I get when r is 5? Substitute r is 5. But remember when this was at 5 squared is 25. by 4 is 100. What you do next? Substitute and you get to go 100 pi multiplied by 0.1. So 10 pi centimeter cube per second. Alright, let's try one here a little bit harder. So a funnel filled with water is in the shape of an inverted circular cone, right? Base with 8 centimeters, height 15. Water is leaking away through a small hole in the vertex at a constant rate of 2 centimeters per second. Let V be the volume of the water in the funnel, and H is the depth of the water in the funnel. Express V in terms of H. How we drawing that in the first place? Same thing that stuff, right? You have a code, right? Put in the radius, right? Water going in. Oh, sorry, it's not leaking. The water coming out. Water coming out at 2 centimeters per second. The radius is 8. I'm just going to fix this piece of the diagram. This is 8 centimeters. The entire height of the cone is 15 centimeters. Right? And it was filled with water, right? And water leaking out of that radius. So that 2 centimeter cube per second is what? Right? dV over dt. Right? So we have that. But we need to get V in terms of H. How are you doing that? What's the volume of a cone? 1/3 pi r squared by H. So express V in terms of H, but you don't want R. So what's it do? Yeah, it's substitute R. Correct. Copy it down and see what you can do. You want the rate of change of depth. Right, so V is equal to what? V is equal to 1/3 pi, R is saying 8, right? 8 squared H. So the equation we have here, how much is 8 squared? That's 64 on 3. 64 on 3H. Part B now, they want the rate of change of height, right? And that's what they want? The rate of change of depth. So that will be dH. Here is dt. Here will be dV. Here will be dV. Right? We already know dV dH. That's this right here. We already know dV dH. Sorry, dV dt. Right? That's the rate of change with respect to time, right? So we know this value, so we need to get this. So since V is equal to 64 pi on 3H, we can make H a subject of the formula. H is equal to 3V all over 64 pi. So if I differentiate H with respect to V, I'll end up with 3 on 64 pi. Right? So therefore, we get 3 on 64 pi multiplied by 2. So I get 6 over 64 pi. This is centimeters per second. That's not right. I feel I used the wrong equation. I feel I used the wrong thing for V. Here's what happened here, right? They want in part B, they want when H is equal to 10. So what that means is that we have to have H in our equation, but when I differentiate of H left, right, something went wrong here. Because what is saying here in our solution, this saying here that the height will always be this, regardless. And V is the original volume. Right? So everything here okay. Everything up until here okay. But they want an equation for volume that will vary with depth. So therefore, I need to find a way to get an equation for R. So I had to find a way to get, so for example, here. Right, so here we have volume at a particular depth h and radius r. So how do I get that equation? So we have v, we want to see how a changing, how to get an equation for r. All right, so here's how we can do. Since what we do original volume, remember v would have been same equation, 1/3 pi r squared h. V would have been 1/3 by pi by r, which is 8, by h, which is 15. This will give us the original volume, right? How much is this? 300 and? Yeah? This is a little tricks in it too, huh? All right, yeah. All right, so here's what you're supposed to do. All right, so what you're supposed to do was the same thing I was saying earlier, right? We needed to get an equation into the r. All right, so we need to get an equation for r and then substitute r there. So here's what we have initially. Initially, we have a cone. You have 8, you have a little right angle triangle there. You see that? And this angle here, as the radius changes, will that angle change? No, the angle won't change. So this angle is what? Tan theta is equal to opposite over adjacent. Okay on that? Yeah, opposite over adjacent. So here now, tan theta is what? Also opposite over adjacent. So it means that this equal to this. So it means that r on h is equal to 8 on 15, which means that r, carry the h here, is 8h over 15. That's okay? Now we know what r is. So as h changes, we know what r is. So now we can come back here and we can say that v is equal to, if I can move this out, 16 squared 15 by 3. So it will be pi by h cubed. What is this here? Pi on 15 squared by 1 2. Right, so you're online. So we're doing something like that to get r, right? What's this here? 64 and 675. So therefore, let's find dvdt and then find dvdh. dvdh, sorry, dvdh is what? 3 here. So that'll be 3 by 64. So that 3 would have cancelled with this 3. So I'll leave it there. So that would be 64 over 225 by pi r by pi h squared. You see what we end up here. Now we can substitute H is 10. So watch. If it's not then substitute H is 10, then I wouldn't get this equation I wanted. Alright? I wouldn't get the equation. I will get the equation, I will get the H value. I'll get the V value when H is 10. I don't want that. I want this equation here, part A. Sure? Huh? So when I substitute, yeah, I'll get dH dt and then I will flip it over. Right? How much is that? So dV dH is equal to 100 by this, 6400 over 225 pi. So it means that dH dV, flip it over, 225 over 6400 pi. And then you multiply 225 6400 pi multiplied by dV dt, which is 2. Right? So what is that? 450 over 6400 pi. That's okay? So you needed this relationship. You needed this relationship in order to find R to get the equation for part A. All right? I made a mistake initially because I get a constant. Right? This is what you're supposed to get because the volume will change as H changes. All right? So generally, if you see a question like this, there is a relationship that you have to get. All right? I just didn't read it. This is the video we're talking about, not the whole volume. The one the volume as a change.